In this video, we will rediscover how computers or calculators perform calculations using simple on and off electrical signals. Let's dive in. An electrical line can either be on or off, represented by a 1 or a 0. So the takeaway is that computers can only represent two states, on and off, using ones and zeros. So how do we use this to perform addition, for example? That's what we'll explore next. We know that we usually use decimal numbers, which are base 10 numbers, which means we have 10 possible combinations, 0 through 9. But in computers, we need to represent numbers using only zeros and ones, which are binary numbers, or base 2 numbers, since electrical wires can only have two states, 0 or 1. So now we need to find a way to represent your regular base 10 numbers in binary. For the numbers 0 and 1, we can represent them as they are in binary, 0 and 1. But what about the number 2? Think about how we can do this. Since we only have two possible combinations, the only way we can represent the number 2 in binary is by increasing the number of digits, and that gives us the number 10. An easier way to think about this is with the list of decimal numbers above. You can see that after 0 and 1, the next possible number comprised of only zeros and ones after 1 is 10, which we can use to represent the number 2 in binary. And then the next possible combination of zeros and ones is 11, which is used to represent the number 3 in binary. Now number 4 will be 100 in binary, since that's the next possible combination of zeros and ones, and so on. With this in mind, let's look at how we could potentially build an electrical circuit for addition. For addition, we would have two input numbers, say A and B. We will then convert those two numbers to binary. Then we will be able to pass those as signals in an electrical circuit. Now, if this electrical circuit was able to give out the result of the addition in binary, that would be problem solved. Now, before we continue, let's quickly review how binary addition works. The rules for binary addition are quite simple. When we add 0 and 0, we get 0. When we add 0 and 1, we get 1. But when we add 1 and 1, we get 10 in binary, which is 2 in regular decimal numbers. This means that we write down 0 and carry over 1 to the next higher bit. Now, for the next bit, we add 1 plus 1 plus 1, which gives us 11 in binary, or 3 in decimal. This means we write down 1 and carry over 1 to the next higher bit. We continue this process for all 5 bits, and we get the final result of 26 in decimal. We call each digit in each of the binary inputs as a bit. So the question is, how do we build a circuit that is able to take in two 5-bit binary numbers as input and output the result of their addition as a 5-bit binary number? To solve this problem, we will first reduce this to a much simpler problem, that of just adding numbers so small that they can be represented using a single bit, 0 or 1. Now let's write down the results of adding single bits in a table. 0 plus 0 should produce 0. 0 plus 1 should produce 1. Same for 1 plus 0. Now, adding 1 plus 1 gives us 10 in binary, or 2 in decimal. But we only have one wire for the sum, so let's add another wire that will give us the carry bit. Now, for 1 plus 1, we will have 0 in the sum bit and 1 in the carry bit. For the other combinations of A and B, the carry line shall remain 0. Alright, so now we know what our end goal is. Build a circuit that will produce these outputs given these inputs. Let's go step by step. We'll first build a circuit only for the carry bit. Now, to get these results that we need, consider the following. If we had two electrically operated switches in series and we connect them to the power supply, then the current will only flow through to the output if both switches are closed. So if we connect A to one switch and B to another switch, then the output will only be 1 if both A and B are 1. Note that there are resistors at the inputs to limit the amount of current flowing through the circuit. We also add a pull-down resistor to ground so that when either A or B is 0, the carry line is pulled down to 0. We have now built a circuit that will produce the correct outputs for the carry bit given any combination of inputs A and B. In modern semiconductors, these electrically operated switches that we used here are called transistors. Now, the circuit that we just built to produce the carry bit is so commonly used that it has a name and a symbol. It's called an AND gate because the carry bit is 1 only when A and B are both 1. Now that we've built the circuit for the carry bit, we can build a similar circuit for the sum bit. I'll spare you the details, but the sum bit can be produced using a similar circuit that uses a different arrangement of transistors, and this circuit is called an XOR gate. So now we have built a circuit that can add two 1-bit numbers. What we've built now is called a 1-bit half adder. Now let's go back to our original problem of adding 5-bit numbers and see how we can use this as a building block to construct a 5-bit adder. Look at the least significant bit of the addition. We are adding 0 and 0, which gives us a sum of 0 and a carry of 0. This is something that our 1-bit half adder can do. Now look at the next bit. We are adding 0 and 1, which gives us a sum of 1 and a carry of 0. This is also something that our 1-bit half adder can do. And now look at the next bit. We are adding 1 plus 1, which gives us a sum bit of 0 and a carry bit of 1. Now let's move on to the next bit, 1 plus 1 plus 1, which is something that our 1-bit half adder cannot do since it can only handle 2 inputs and not 3. To be able to handle this case, we will need to build a slightly more complicated circuit called a 1-bit full adder. So now, to build a 1-bit full adder, we will need to be able to take in 3 inputs, A, B, and the carry bit from the previous addition, and produce a sum and a carry output. For this, we take in the 2 inputs A and B and feed them into a 1-bit half adder to produce an intermediate sum and carry. Then we take the intermediate sum and use another 1-bit half adder to add it to the carry in bit, which produces the final sum bit and another intermediate carry bit. Finally, we take the 2 intermediate carry bits and feed them into an OR gate to produce the final carry out bit. The OR gate also consists of a bunch of transistors, but I won't go into the details of that circuit since it's similar to the AND gate circuit that we built earlier. All you need to know is that the OR gate produces an output of 1 if either of its inputs is 1, which is what we need for the carry out bit. Let's update our truth table for the sum and carry outputs, given that we have 3 inputs now instead of 2. For the case that all 3 inputs are 1, let's see what happens. A and B go through one half adder and we get outputs of 0 and 1 at the sum and carry outputs. Then in the other 1-bit half adder, we have inputs of 1 and 0. So for the second 1-bit half adder, we have an output of 1 for the sum bit and 0 for the intermediate carry. And finally, the OR gate connected to both the carry outputs will output 1 since the first half adder's carry bit is 1. So the final sum bit is 1 and the carry bit is also 1, which makes sense since 1 plus 1 plus 1 equals 3 in decimal, which is 11 in binary. So the sum bit is 1 and we carry 1 to the next bit. Similarly, we can fill out the rest of the truth table for the sum and carry outputs given all the combinations of inputs A, B, and carry in. And with that, we have successfully built a 1-bit full adder circuit that can handle the addition of any 3 bits and produce the correct sum and carry outputs. And with that, let's now go back to our 5-bit addition. We take a 1-bit full adder and input the least significant bits of the addition. The first carry-in bit is always 0 since there is no previous addition. We get a result of 0 for the sum and carry bits when both A and B are 0. For the next bit, we bring in another 1-bit full adder and we input the next least significant bits of A and B along with the carry bit from the previous addition. We repeat this process for all 5 bits, cascading 5 full adders together, and we get the final result of the addition at the end of the chain. And this chain of 5 1-bit full adders is exactly the 5-bit addition circuit that we set out to build from the very beginning of this video. Now, a 5-bit adder can only produce sums up to 31, the largest 5-bit number, but modern computers simply extend this circuit to 64 bits, enabling addition of numbers with sums up to over 18 quintillion. And that is how computers add numbers. As a side note, as the number of bits increases, the delay from the carry bits propagating through the chain of adders also increases, which is why modern computer architects have designed more complex adder circuits that can compute sums faster by reducing this carry propagation delay. But that's a topic for another video.
So far, we've used AND, OR, and XOR gates to build an adder circuit, but there are more logic gates in the engineer's toolbox. Here are the 6 fundamental logic gates: AND, OR, NOR, NOT, NAND, and XOR. Each of these gates is built from transistors, just like the ones we explored earlier.
By combining these gates in different arrangements, engineers can build circuits for virtually any arithmetic operation. We already saw how AND, OR, and XOR gates combine to form an adder. Using similar techniques, these same gates can be wired together to create a subtractor, a multiplier, a divider, and even circuits for comparison and other complex operations.
In fact, all of these individual circuits are combined into a single unit inside a processor called the Arithmetic Logic Unit, or ALU. The ALU is the part of the processor that performs all arithmetic and logical operations, and it is built entirely from logic gates, which are in turn built from transistors. And that is how calculators and computers perform calculations, all starting from simple on-off switches.